Hi, welcome to this lecture. Today, we are going to be learning about Scikit-learn. Scikit-learn is one of the most popular machine learning libraries in Python. If you are a complete beginner, I'm sure you're going to enjoy this. If you have spent a little bit of time in machine learning, there is a very high chance that you have already heard of Scikit-learn. But in either case, we will go ahead as if we are complete beginners. So at the end of this lecture, I'm hoping to cover fairly good amount of details about the machine learning pipeline. Specifically, how do you explore the data set? How can you implement maybe two different types of machine learning models on that same data set to make predictions? And how to do all of this using scikit-learn library. And today we'll be implementing k nearest neighbors and decision trees. So as part of the implementation, I will also discuss a little bit of the theory behind how it works. And we will see how to pre-process the data a little bit, how to perform evaluation of the model. And at the end of the day, you will get a feel for implementing the end-to-end machine learning project pipeline. Of course, the data set will be very simple today. So you don't have to worry that the model that we are going to be implementing is something that is complex. That is not the case. So with that being said, let's get into the lecture. So before entering into scikit-learn library, let's briefly discuss what exactly is machine learning. So in machine learning, we don't explicitly program for the output, right? Whereas if we are writing if and else conditions, if the condition is this, then this is the output. Else if this is the output. Else if this is the output. Else this is the output. So in conditional programming, we explicitly define the condition for which you need the specific type of output. In machine learning, we don't do that. We let the algorithm figure out what the conditions should be and what the output should be for a given input. So this is why it's called as machine learning. The learning of these conditions happen during the process of something we call as training. So there are three types of machine learning learning process: supervised learning, unsupervised learning, and reinforcement learning. There are also other terms like self-supervised learning, semi-supervised learning, etc. So in supervised learning, for example, if you are teaching the model to classify a set of images into dogs versus cats, then you will have images as the input data and corresponding labels. Label meaning whether an image corresponds to a dog or a cat. So that's called label data. And this is fully supervised learning because you have images and the corresponding labels. In unsupervised learning, you don't have explicit labels. So if you want to create clusters out of a data set, you can run an unsupervised machine learning algorithm to perform the clustering. You have no idea how many clusters are there. You have no idea which data point belongs to which cluster, but clusters are automatically created. And this can be used in, for example, if you want to group your customers, if you are running an e-commerce website similar to Amazon, and if you want to group your customers into highly like people who are potentially likely to spend on something versus who are not likely to spend on something versus something else. Or even if you want to discover the types of customers, for example, and you don't know how many types are there, then it's an example of unsupervised learning. In reinforcement learning, you make the algorithm learn via rewards or punishments. So you may have seen videos on YouTube like teaching an AI agent to run faster than Usain Bolt, or teaching an AI agent to walk. So these things are done via reinforcement learning. We also have done a video on using reinforcement learning to teach a snake. You have played the snake game. So teaching that snake to go correctly so that it can eat that apple and increase its length. So, and then one more interesting example could be self-supervised learning. So in large language models like GPT, the way it works is you have input data in the form of text from internet, and the set of words before a particular word or before a particular token is used to predict that token. So if you have 10 tokens or 10 words, to make it simple, you use the first word to predict the second word. You use the first and second word to predict the third word. And then you use first, second, and third words to predict the fourth word. Like this. So here it's like self-supervised because labels are present in the input dataset itself. So these are some types of machine learning models. And today we'll be looking at supervised learning. using Scikit-learn library. But the general ML workflow we can write like this. So first process is data collection. So data collection can happen through experiments which you conduct in real world. It could be if you are running a website and if your data comes from the customers, you may be running some API calls to fetch the data after it is saved in your backend. Or you may have data already given to you by someone in a CSV file. For toy projects, you can get a lot of data from Kaggle or other websites. And then you pre-process the data. So you can't use the data as such because it will be unclean. There will be missing values. There will be columns which are completely useless if it's a tabular data. There will be cells in which there are no values or sometimes not a number or extremely high numbers, big numbers. So there are so many issues that can happen in a data set. So you have to pre-process and clean the data. Then in supervised learning, you split the data into training and testing so that the training data set you use, you expose it to the model so that the model can learn. Testing data is used for kind of verifying the general capability of the model. So in testing, if the model can perform as good as it performed during training, then it's a sign that you don't have an overfit model, you have a good model if the testing accuracy and training accuracy are both good. Then after the splitting, right, you perform the training on trained data and then you evaluate the model. So there is test data set, trained data set and validation data set. So you train your model and you validate it. And then if you are part of a competition, machine learning competition, you will have a model which you can, first you will have a data set. So you split your data set. A part of it is used for training, maybe 20% is used for validation. Once you are confident that your model can perform well on unseen data, which is the validation data, you can submit it for testing. And then whoever is conducting the competition can test your model with another set of unseen data. And if it performs well, you have a good model, you may win a prize. So this is sort of how competition works in real world. Of course, you can do something similar before you deploy your model for a production level usage. You have to test your model on unseen data. And then finally, after you build your model and evaluate your model, you can try to derive inferences using your model from new data, right? So this is the general machine learning pipeline. So today in Scikit-learn, we will use this library for a specific problem, and we will try to implement most of the steps discussed above. So let us try to understand what is Scikit-learn. So as I mentioned, Scikit-learn is probably by far the most popular machine learning library in Python. It's not as popular these days as, let's say, TensorFlow or PyTorch. But Scikit-learn, I'm sure as a machine learning beginner, this is one of the best places to start with if you are trying to implement some simple models for simple data sets. It's built on top of NumPy. So we have discussed in one of the earlier lectures on NumPy that NumPy made Python better because the native Python lists for handling arrays was not good. It could not perform vectorized operations, but NumPy could perform vectorized operations. So NumPy is one of the most important libraries in Python that made the entire programming language popular among data scientists. And then on top of it, Scikit-learn was built, Matplotlib was built, SciPy was built. So all of these libraries made Python one of the most attractive programming languages for machine learning people as well as for data scientists. In Scikit-learn, you will get access to various models, various machine learning models. You can perform fitting on the training data. You can perform prediction on validation data. You can perform pre-processing on data set, which we will do today. We can perform model evaluation like precision, recall, accuracy, and we can build such machine learning pipelines for performing this whole operation. So let's start implementing Scikit-learn by looking at a very simple data called as iris data. So this iris data is that of a set of flowers called Setosa, Virginica, and Versicolor. It's very famous data set. I'm pretty sure if you have done some projects on Kaggle, you have come across iris data set. So if you Google iris data set and if you look at the image, this is basically the description of the data. You have 4 parameters of the flowers. I'm just opening this article. So you have something called as sepal, and petal, and you have width and length of each of these. So you have petal length, petal width, and you have sepal length and sepal width for 3 category of flowers: iris, setosa, versicolor, and virginica. So now the problem is, how can you build a classification model which will allow you to identify whether a flower is setosa or versicolor or virginica based on its sepal and petal width and length. So this is the goal here. It's a very simple and very popular data set, and let's see what we can do with this data set using scikit-learn, and how can we implement a very simple machine learning pipeline on this data set so that you can apply pretty much the same thing on even more complex data sets. Whether you're a student working on a let's say classroom assignment, or whether you are performing an internship, or whether you are working in a job, the basic structure of the pipeline would remain pretty much the same. So the first step is you import scikit-learn, and so from sklearn is scikit-learn. Here we are first importing the data set. So we are loading the iris data set. So let's do one thing. Let's open Google Colab Notebook. So go to collab.research.google.com and click the new notebook, and then it will open a new notebook. And first thing is importing the library. So from sklearn.datasets, import load iris. So here I will title this as intro to scikit-learn. All right. And then iris, we are naming the data frame as iris equal to load iris. So this will load the iris dataset once the Google Colab Notebook connects with the Python backend. So next, what we need to do is create a pandas data frame in which the iris dataset is loaded using this variable called iris. All right. So that is what is done in this code. So first we import pandas. So let's do that. So import pandas as PD, and then we say X, which is the training data set values, and Y are the corresponding labels. So here X is equal to pd.data frame. So we are converting the iris.data into a data frame, and the column names are basically the features, and features are sepal length, sepal width, petal length, and petal width. So let's copy this line. So X equal to this, right? So if we run this code, and now if we want to display this, the top 5 rows of this data frame, all we need to do is like x.head. So this will show the first 5 rows of this data frame. And you can see that the columns are the features I mentioned earlier: sepal length, sepal width, petal length, and petal width. Then we need to also say Y equal to pd.data frame. And here it should be target, right? So iris.target. Oh, this is a series because there is only one feature, just the target. So iris.target. And here you can also print Y. So Y looks like this. So this 0, 1, 2, 3, etc. are the index of the each element, and the values will be either 0 or 1 or 2 corresponding to each flower. So there is Setosa, Versicolor, and Virginica, right? So now we have the names of the flowers stored as labels in this Y, and we have the data set, which is the length and width of petal and sepal, stored in X. So we have our data set ready. I just run it once. All right. Now what we can do is we can make a copy of X. X is the input data and Y is the input data label. And we can create a new data frame. And in the new data frame, we can add an extra column called target. And the value of that target could be the value of the Y. So I'll show you what I mean. So df equal to X. We can make a copy of X. So X is converted to a copy, and then df of target. So this means a new column called target will be created, and that is equal to Y. And here, if we say df.head, it will not have 4 columns. It will have 5 columns. 5th column will be this target. So 1, 2, 3, 4, 5, right? So now 5th column is the target. Target, as I mentioned, will be 0, 1, or 2. All right, so now we have our final data frame ready, which is stored as variable df. And this data frame is what we will use for training our model. So first we have to also visualize the data set a little bit before we even split into training and testing data, and before we even decide what machine learning model to use, right? So first, let us see how the data set distribution looks like. How many flowers are there in each category? What are some relationships between sepal length and the flower category, or petal width and the flower category, etc. So that we have a visual intuition of what this data set is about instead of blindly implementing a model. So that is the next step. We will be visualizing the data set structure, like class distribution, or feature relationship, pairwise, univariate plot, etc. So let's see how to do this using Scikit-learn. So first, because this is a statistical plot, we will be using Seaborn for making the plot. So we can import the Seaborn library, import Seaborn as SNS. All right. And then what we can do is there is sns.countplot. Countplot will give us how many counts of unique items are there in a particular, corresponding to a particular label. So sns.countplot, and x equal to iris.target. So x-axis value is iris.target. In fact, iris.target is one thing which we can use. Otherwise, I think we can just use df of target. Let's see. First, we can plot like this. So iris.target. So there are 50 flower images in each category. That is what this says. The flower with index 0 has 50, index 1 has also 50 items, and index 2 also has 50 items. So there are total 150 images in this data set. I think we should also be able to do like df of target. Let's see. Yeah, df of target also works because df data frame has a new column called target, and then that also gives us pretty much the same thing. Okay, and then we could add plot title, the x-axis label, y-axis label. So let's do that. So plt is from matplotlib. So import matplotlib.pyplot as plt, and class distribution should be the title. So just this much is enough. And target class is 0, 1, 2. So that should be the X label. Y label is simply the count. So that is what this is. So this is the count distribution plot. Now you can plot another thing like pairwise feature relationship. So pairwise feature relationship is how does the, for example, sepal length correlate with the class. So this is how the plot finally looks like. I'll plot it once, but let us first go through the graph initially. So here there are 4 features, right? Sepal length, sepal width, petal length, petal width. And that is what you see here on the 4 x-axis here. You have 4 y-axis here, which is again petal width, petal length, sepal width, and sepal length. So the first plot over here, this one, is sepal length versus petal width, and the colors are corresponding to target. So you can see that the flower corresponding to target as 0, it has generally the lowest petal width. So if you want to classify flowers into, let's say, category 0 or any other category, then all you need to do is like set a cutoff for petal width to be like 0.75. So anything below 0.75 will be flower category 0. Otherwise, it will be category 1 or 2. Here also you can see this is petal length versus petal width. So if you say petal length cutoff is something like 2.5, then anything below that will be flower category 0. Otherwise, it will be category 1 or 2. So this is the class distribution pairwise plot. So let's plot this actually. And the hue, if you don't have hue, I'll show you what happens. So let me first copy the code and paste it here. So we are plotting pair plot on the data frame. Let me first remove this hue, and corner also let me remove, and subtitle. Okay, so this is now the plot, right? But here you don't see different colors. You don't see the three colors because we have removed the hue option. So let me put back hue equal to target. And where is the target taken from? Target is taken from whatever is the input data. So inside input data, there is target. So if we add hue, then you will see three colors. So the same data set which was plotted using blue color is now plotted using based on the class. So class 0, class 1, class 2. So I don't think the corner thing is really needed. So here sepal length, sepal width, petal length, petal width, and everything as you see here. So from this graph itself, you can already see that which flower is the shortest along the petal, which flower is the shortest along the length or width of the petal. And clearly class 0 is well separated from class 1 or class 2. And here also you can see if you plot petal length, it's like a tri-model distribution. So this is the first this set of distribution. This is the distribution of the other flower. This is the distribution of the other flower. Clearly there are three modes. But you can also see that for flower of category 0, it's very, very well separated from the other two flowers. So clearly you can see that petal length is a feature that you can use. Can you use sepal width? Here, this is the sepal width, and you can see that sepal width is not that easy because if you try to classify flowers using sepal width as the feature, they are overlapping pretty much. So all the three flowers have very similar sepal width distribution as you see like in the overlap of these three plots. So these kinds of informations you can get from this plot like pair plot. That is also from Seaborn. So next, correlation map. So correlation map will give us how a feature is correlated, whether it's positive correlation or negative correlation with the output. And what is the output here? Whether it's 0, 1 or 2, right? So let's plot it. So is it sns.heatmap? And we are making df, data frame df, and dot correlation means we are calling the correlation function. So before looking at this correlation heat map in detail, let's try to predict whether the heat map cell value will be negative, whether it will be a big negative number or small negative number, just by looking at this pair plot, right? So in the pair plot we had earlier, you can see that the target value reduces as sepal length reduces. So this has target value 0. You can see that here. These set of flowers have target value 1. These set of flowers have target value 2. So you can say that target value increases as sepal length increases. That is clear, right? And target value increases as petal width increases. So you can say that sepal length and petal width should be positively correlated with the target. So let's see if that is true or not. And also one more thing, sepal length value range is going from 4 to 8 here, and this is going from 0 to 2.5. So I think it's hard to predict the magnitude, but definitely petal width with target and sepal length with target should have positive number. Let's see. So petal width is here. And then what was the other one? Second one was sepal length. Sepal length is the first one. Sepal length and target. So sepal length is the first row. Target is the sepal length and target is this number 0.78. And you can see that it's a positive correlation. Similarly, petal width and target is 0.96. Again, a very, very positive correlation as we predicted. Let's see some other number. Now, what about sepal width versus target? As sepal width increases, target value is becoming 0. But here for flower number 2, it's hard to say. If you compare flower with target 1 and flower with target 2, it's hard to say whether there is a direct proper correlation between sepal width and the target number. So in general, I feel like this will be a small negative number. Why is it not a big negative number? Because it's not like as sepal width decreases, the flower target will go from 2 to 1 to 0. That correlation is not that strong, but definitely when it goes from 2 or 1 to 0, that correlation is very clear because 0 is well separated in terms of sepal length somewhat. So I would say my prediction is sepal width would have a slight negative value as the number inside the cell when you are comparing with target. Let's see, sepal width versus target is minus 0.43. So the value of absolute value of 0.43 is less than 0.78 or 0.96, the earlier two numbers. and it's negative. So our inference is correct. We can also look at one more number, maybe. Let's see, petal length. So here petal length is definitely positively correlated. So petal length should have a very big number, in fact, because the range is from 1 to 7. As petal length increases, definitely the target changes. So let's see petal length versus target. Yeah, see, petal length versus target is 0.95. Very, very good positive correlation. So this is the meaning of this correlation heat map. If it is positively correlated and if the number is big, it means if one value increases, the other value definitely increases. If the correlation value is close to 0, it means the correlation is vague. So here sepal width versus sepal length correlation is minus 0.12, meaning there is no really any that much correlation between sepal width and sepal length. Right. So this is a very good way to, whereas, for example, petal width versus petal length is very high positive correlation, meaning if a flower has big petals, I mean, wide petals, its length also will be very high. That's why this number is 0.96. So these kinds of correlations you can get from the heat map plot. All right. Now let us move on to pre-processing the data, because in our data set there could be many issues. So before even we implement the machine learning model, we mentioned that we have to look for issues in the data set and we have to perform pre-processing. So let's do that first. For the scikit-learn, for the iris data set, the first pre-processing is simply creating the training test split, because there are no empty rows or empty cells in the data set. So it's a very clean data by default. So let's first call the train test split function from scikit-learn and use that to create training test data set separately. So from sklearn.model selection. So this model selection has train underscore test underscore split, and that function we will use with x as the input values, y as the input target. Then test dataset will be 0.2 and remaining 0.8 will be training. And random state equal to 42 decides how the split happens. So if you don't specify the random state, basically you won't be able to repeat the train test split. But if you want repeatability with randomness, you can specify the random state. But basically, this will create the data set for training and testing, labels for training and testing. All right. So let's run the code. It will not display anything because this is just creating the data set. Next is scaling the data set. Scaling meaning this is a part of sort of like normalization. So if you Google batch normalization, for example, the data set originally may have, if you just look at this graph, originally the data set may have some mean value and some standard deviation along various features, right? Like this. But then with normalization, so this image is showing batch normalization, but basically in normalization, what happens is mean value becomes 0, standard deviation becomes 1, right? So that's what we do with scaling the data set. So here, scaling the features means the training data set will be scaled such that mean value is 0 and standard deviation is equal to 1. So let's do that also. And this, in fact, makes the model performance very, very much better. And I have experienced this in multiple projects. So scaling the data set here, we use this standard scaler function, which is again built in the scikit-learn library. So scikit-learn sklearn.preprocessing, and from that we import standard scaler, and we define the scaler by calling the standard scaler function, and then we implement the scaling on training data and testing data. Labels need not be scaled because labels are anyway the target, right? 0 or 1 or 2. So let's execute this code as well. Now what we do is we can have a visualization of the feature distribution before scaling and after scaling. So before scaling, this is, for example, how sepal length was distributed. It was distributed from like around 4 till 8. That was the distribution, and mean value was somewhere in the middle, like 6 or 5.5 or something. After scaling, you can see that mean value is now close to 0 and standard deviation is like close to 1. You can't see the standard deviation from the graph. The range is of course -2 to something like +2, but standard deviation is less than that. But mean value is something close to 0. So this is what happens to the data set after scaling. So let me just run this code and show you the data set before and after scaling. And I can show you maybe different things. Not just the sepal length and not just the sepal length. So this is before and after scaling the data for sepal length. We can also do the same for another maybe sepal width, I guess. So this is sepal width, right? So it goes from 2 to 4.5. Let me look at the pair graph which we plotted earlier to make sure that sepal width has indeed the correct range, because then I can know that the plot that I made, the plot label that I made is correct. So sepal width goes from something like 2 to around 4.5, right? That's exactly what we have here. So originally, this was the range of sepal width, but after scaling, you see the mean value center is 0, and the range is from -2 to 3. So it's a range of around 5.5, because here it goes from, this is 3 and this is around -2, so that is 5 plus around 0.5. So, but the standard deviation will be 1. So this is what happens to different features after scaling. If scaling was not done, feature values will remain as such. And sometimes, for example, here petal length can go up to 7, whereas for example here, so for this flower, right, petal length can go up to 7. But if we look at, say, petal width can only go till 2.5. So petal length as a feature, its maximum value by default is 3 times more than petal width as a feature, its maximum value. So that is not good as a data set. So you can normalize it. And that's exactly what we are doing here with scaling function. All right. So this is another type of pre-processing that you will have to do irrespective of what machine learning model you are building. Now let's talk about two models, k nearest neighbors and decision tree. So these are the two models we are implementing today on this iris dataset. So k nearest neighbor as well as decision tree are two ML models. You can get the model building as well as training, everything as functions defined within Scikit-learn library. So first, let us learn about KNN, k nearest neighbor. So the idea is very simple. Let's say you have two features, maybe your age and your school name. And let's say a new student is there, and let's say the data of all the students in some schools and some age groups are available about whether they like cricket team A or cricket team B. Then if you want to predict for a new student whether this student will like A or B, all you need to do is look at the features, look at the age, look at the school name, and see which other students are closest to them. If the closest neighbors, if k closest neighbors to them are mostly belonging to, let's say, fan of cricket team A, then most likely this student will also be a fan of cricket team A. Another example is what I have shown here. So let's say based on size and color, you want to distinguish a fruit, whether it's apple or orange. Then if you have size and color plotted on an axis, and if a new fruit is given, and let's say that new fruit is this guy, you look at the k nearest neighbors in a certain neighborhood. And if those neighbors are predominantly apple, then this new unknown fruit of this particular color and particular size will also be apple. Otherwise, it will be orange, right? If four of them in the neighborhood are apples and one is an orange, then the new fruit is probably an apple. So this is the idea of k nearest neighbors. And this idea can be extended for multiple dimensions also. Because in our case, we have 4 dimensions: sepal length, sepal width, petal length, and petal width. So it can't be obviously plotted on 2-dimensional graph. It will require 4 dimensions. But there also you can define a hyperspace, a 4-dimensional space around any given data point. And using that, we can predict whether a new point belongs to Versicolor, Virginica, or Setosa, right? So that's the idea behind KNN, k nearest neighbor. So implementing KNN in Scikit-learn is fairly easy. So from sklearn.neighbors, you import k-neighbor classifier. So this is the import that you have to make. So see how easy it is, because all these ML models are predefined in Scikit-learn. It makes your life so much more easier. And then you simply say the KNN model is k nearest neighbor classifier with, you're looking at n equal to 3. You are looking at 3 nearest neighbors. And then you are fitting on training data and training labels, and then you are making predictions on the test. So this That's it. You basically did the machine learning model training on your training data and testing data. Remember, you had 150 data points, 80% of them was for training, 20% of them were for testing. And we can see the test accuracy. But before going to see the test accuracy, let's also discuss about one more ML model, which is decision tree. Decision tree is also fairly straightforward. In decision tree, the way it works is it's by splitting the data set by maybe asking some questions or looking at feature threshold. So let's say you have three type of animals, say cow, pig, and dogs. So this is a graph where this is height and this is weight. And let's say cows are taller and they are heavier. So let's say these are all cows. Okay. In general, cows may belong to this area. Dogs are generally a bit shorter and their weight is also generally less. So maybe these are all dogs. And pigs, maybe height of the pigs are same as dogs, but they might be heavier. So maybe pigs can belong to this place. Okay. So here in our annotation, these are pigs, these are cows, and these are dogs. Now, the way we can construct a decision tree is first start with a node. In this node, all of the data set will be available. So let me just create a copy of the data set like this. So this whole data set is available at the first node. Okay. And now this node has to split the data set into some parts. Okay. So the question here in this node could be, is height greater than, and let's say this is maybe 2 feet or 3 feet. Is height greater than 3 feet? Is h greater than 3? Then if it is yes, those data points will go to the right hand side of this node. So this is the yes branch of the data set. And so all the cows will have height greater than 3 feet. So let them be here. All right. I'm sure this number is wrong, but I'm just giving you an example. And is there a need for splitting this any further? No, right? Because you only have cows here. You don't have to split cows again, because your only goal is to split animals into cows, dogs, or pigs based on height and weight. Now, among the animals with height, so this is yes. Traditionally, yes is on left and no is on right. So maybe I'll follow that. So this is no. And this is on the left hand side, it is yes. So I'm going to move this here. Okay. And in the no category, all the remaining data points will go. All right. So all these data points will go to the no branch. So let me bring it here and just make it small. All right. So now these data points can be further split. Why? Because these set of data points have both dogs as well as pigs. Now, how can you split dogs and pigs? You can split them using weight. So maybe the weight cutoff here is 8 kilogram. I don't know. Okay, I'm just making up a number, but let's say the question then we ask at this node is weight greater than 8 kilogram? And if that is true, so these are now cows. If weight greater than 8 kilogram is true, then that is all of these points, right? Basically pigs. So all pigs will come to this this node, and all the dogs over here will come to the node known branch. So this is the no branch, and so this is no, this is yes, or rather true or false. So weight greater than 8 kilogram, yes. If yes, these are pigs, and these are dogs. So now if a new animal is given whose category is not known, whether it's a pig or cow, then all we need to do is like, okay, let's say the animal is over here. I don't know whether this is a pig or cow or dog. Then first we check, is the height greater than 3? Is the height greater than 3 here? No, it is not. So then we have to go to this branch. Then the next thing we have to check is weight greater than 8 kilogram? Is that true? Yes, weight is greater than 8 kilogram. So then we go here. Then we say that this new animal is a pig. So this is how basically decision tree works. And of course, constructing these thresholds, it's a separate process involved in training. But all of this, what I mentioned, can be easily executed using Scikit-learn, right? So basically the decision tree splits the data set into subsets by using feature thresholds. Here, the features were height and weight. In some data sets, there will be more features. In our iris data set, we have 4 features. All right. So let's implement the decision tree to classify our flower data set. Okay. So I'm copying the code. So from scikit-learn.tree, we implement decision tree classifier. Maximum depth equal to 3 means you have the parent node, then another layer of 2 more nodes, and then another layer of 2 each more nodes. So that is maximum what will happen. And then we are fitting the tree on training data and corresponding labels, and then we are making predictions. It's very easy to, even if you want to implement decision tree from scratch without using this library in library of scikit-learn, that's also very much possible. But it's not needed because it's available already. Now let us evaluate these two models. So we have decision tree model and k nearest neighbor model. So let's visualize how well the model has performed its fitting and how well it can make prediction on test data set. So here for model evaluation, we are creating confusion matrix plot. Okay. So here is the confusion matrix plot. So what you see here is actual label versus predicted label. So if actual label is 0 and if predicted label is 2, it means you made a mistake. Similarly, or this is the opposite. Actual label is 2. So here the value is 0 means for no flowers, the model made a wrong prediction, which is the model here, KNN confusion matrix. So the KNN model, K nearest neighbor model, did not make any single mistake. So basically, if a flower is actually 2, they were not misclassified as class 0 or class 1. They were all classified as class 2. So in the testing data set, first of all, we had 150 data points, out of which 0.2, which is 30 data points were used for testing. So sum of all these three should be 30. So 10 plus 9 is 19, 19 plus 11 is 30. So out of 30, because we were splitting randomly, 11 of them are belonging into class 2, 9 of them are belonging to class 1, and 10 of them are belonging to class 0. And all these flowers have been classified accurately. So here, because the false predictions, all these values are zeros, here the testing accuracy is 100%. Now let's look at decision tree. Decision tree also makes 100% accurate prediction. You can see that none of the flowers who are actually 1 or 2 are misclassified, or even 0 are misclassified. All of them are correctly classified. We can make this worse. Maybe instead of looking at 3 neighbors, what if we look at 2 neighbors? And similarly, instead of looking at tree of depth 3, what if we reduce the depth? Maybe the accuracy will reduce, we'll see. So now I have implemented, see, now there is a misclassification. KNN is still working perfectly, even though I have reduced the number of nearest neighbors, but decision tree has made one mistake. So here, for this one, whichever this data point is, the actual label is 1, but the predicted label is 2. So that mistake it has made, but all the other predictions are correct. So decision tree made this mistake because maximum depth allowed is only 2. What if we make it 1 and here also 1? Then the predictions will become even worse because now this is not at all a complex model. See, so KNN, now it's looking at only one nearest neighbor. KNN is still performing really well, surprisingly. Whereas our decision tree now has made a lot of mistakes. Let's see. So if a flower is of class 0, all of them are being predicted correctly. And I showed you in the pair plot, right? Class 0 is very easy to predict. Why? Because if you remember, class 0 had very small petal width. You see, class 0, this is class 0. It has very small petal width and it also has very small petal length. So class 0, there will be no confusion. But class 1 and class 2 can get misclassified. So here you can see that for class 1, 9 of them are actually, this is a very good thing. 9 of them are actually predicted as 1. So there is no mistake in class 1. But class 2, every single flower has been misclassified as class 1. Not a single flower entered class 2, right? That's because we don't have depth. We are looking for a 3-class classification, but we are allowing only depth 1 for the decision tree. So that's why this happens. So this is again a way in which you can build machine learning models with just few lines of code, right? Here we built KNN and decision tree. So this is the power of Scikit-learn library. You will definitely use this if you are working on basic machine learning models. And here is the visualization. And we can also create a classification report in terms of accuracy, precision, recall, etc. So let's do that also. So the report will involve precision, recall, F1 score, and accuracy. So accuracy for our current model is 1 for KNN. KNN is still perfectly working. None are misclassified. But for decision tree, we can calculate the accuracy. There are total 30 points to classify. 11 of them are misclassified. So accuracy is 19 divided by 30. What is this? 0.63 in the testing. So let's see if that is the case. 0. Precision accuracy is 0.63. You can see that here the accuracy was 1. So what we are calculating is correct. So this is how the model building or model development for a machine learning pipeline works using Scikit-learn library. Of course, I'm fully aware that the sample data set that we have selected is the simplest data set, but that is to make sure that this lecture is beginner friendly. I highly recommend you to try something very similar for more complex data sets where classification is not so obvious. Here, it was kind of obvious. It's not that hard to classify these 3 flowers based on looking at the length and width of sepal and petal. But I hope you got a fairly good idea of how machine learning pipeline construction works, starting from loading the data, pre-processing it, visualizing it to see how it looks, creating the train test data split, defining the ML model, training it, testing the model on test data set, visualizing the performance in terms of confusion matrix, and then looking at the classification report in terms of accuracy, precision, recall, F1 score. So with that, it's a good time to wind up this lecture. Thank you so much for listening. We'll again meet in another lecture. Take care until then. Bye.